Hello friends, welcome to Kranthi Physics Tutorials. Okay, so today we have in this class we have to discuss one of the most important question in your second year physics, intermediate physics, that is Wheatstone bridge. Wheatstone bridge. So already in the last classes, previous classes, so we had to discuss about the Kirchhoff laws. Kirchhoff laws. So the application of Kirchhoff laws is called as the Wheatstone bridge. So in your IPE examination or JEE NEET examination, in your IPE examination, so they are combinedly asked Kirchhoff laws and Wheatstone bridge. So both the questions are combinedly asked as a long answer. So that's why one of the most important questions in your entire second year textbook. This is Wheatstone bridge. So here you must and should remember the Wheatstone bridge is the application of Kirchhoff laws. Wheatstone bridge is the application of Kirchhoff laws. So Wheatstone. So Wheatstone bridge. Wheatstone bridge. What is that? Wheatstone bridge. So here Wheatstone is the scientist name. Wheatstone is a scientist name. Wheatstone is a scientist name. Okay. So now let me go to the top. Let me go to the top. Okay. So Wheatstone bridge has 4 resistors like a bridge, like a combination of. So Wheatstone bridge has combination of 4 resistors and it's look like a bridge. That's why this is called as the Wheatstone bridge. So here I can draw the diagram of the Wheatstone bridge. So let you see. Okay. Okay, so Wheatstone bridge has 4 resistors. So R1, R2, R3, R4. Wheatstone bridge has 4 resistors. R1, R2, R3, R4, and these junctions can be taken as A, B, C, D. So here it has 4 junction points A, B, C and D. So it has 4 resistors and 4 corners A, B, C, D. So from junction B to junction D, in between the junction points B and D, we can connect the galvanometer. We can connect the galvanometer. So from the opposite junction points B and D, so in between B and D, the opposite junction point, we can connect the galvanometer and the remaining opposite points, in between the remaining opposite points AC, we can connect the high resistance battery. This is the symbol for high resistance battery. So Wheatstone bridge has 4 resistors R1, R2, R3, R4, and we can connect the galvanometer in between the 2 opposite junction points B and D, and the remaining in between the remaining opposite junction points AC, we can connect the high resistance battery. So now this diagram, this circuit is looking like a bridge. That's why it is called a Wheatstone bridge. So Wheatstone bridge. Okay. So here from the positive terminal, the current is passing in this direction, and here 2 ways are there at junction at point A. So that's why the current will be splits into 2 direction. So here for R1 I1, for R2 I2 current, and the current goes like this, and it will be here I4. But here the I1 current is so passing like this, and at point D the I1 again splits into two currents. So that is, one is the galvanometer current Ig, and another one is the I3. Another one is the I3. So here first of all, from the positive terminal of the battery, the current I is passing from the positive terminal of the battery, and it reaches the point A. At point A, it will be splits into two currents, I1 and I2, and the I1 current is again splits into two currents, that is Ig galvanometer current and I3, and the I2 is here through the R4 I4 current is passing, and finally at point C, so all the currents are mixed up, and the total current, the initial current I will be remain reached to the negative terminal of the battery. So now the total circuit will be completed. The total circuit has been completed. Okay. So first from the positive terminal, current I is passing, and it will be splits into I1, I2, Ig, I3, I4, and again the total current I will be reached to the negative terminal of the battery. So now the total circuit has been completed. Okay. So this diagram, this circuit is looking like a bridge. That's why it is called as Wheatstone bridge. So now we have to derive the balancing. We have to derive the balancing condition of the Wheatstone bridge. Through this diagram, we have to derive the balancing condition. So what we derive? Balancing. So balancing condition. So balancing condition for the Wheatstone bridge. So now we have to derive that equation. Okay, balancing condition. So here, so point A and point C, or point A and point C are not the junction points, only point B and point D are junction point. Mean point B and point D, these two are only junction points. A, C are not junction points. Why? Because so if two ways are joined at a point, that is not called as a junction. So minimum three ways are joined at a single point, then that is called junction point. So here at point A, only I1, I2, only two ways are there. This is the main circuit, so you don't bother about this one. So at point A, only two ways are there. At point C also two ways are there. But at point B and point D, so three ways are there. At point B, so I2, Ig, I4, and at point D, I1, I3, Ig. So three ways are there. So that's why only the point in this circuit, only the point B and point D are called as junctions, considered as a junction, but not the AC. So that's why, so here now we can apply the, so Wheatstone, already I told that Wheatstone bridge is the application of the Kirchhoff laws. So that's why now at point junction points B and D, we can apply the Kirchhoff's junction rule. So Kirchhoff's junction rule can be applied at junctions B and D. So we can apply the Kirchhoff's junction rule at the junctions B and D only. So not at AC. Why? Because AC are not considered as a junction points. Okay. So here, first of all, we can apply the Kirchhoff's first rule at point B. So you can place your finger at point B. And look at the currents. So the I2 current is entered into the junction B. I2 current is entered into the junction B. So therefore the I2 can be taken as positive, and Ig current is also entered into the junction B. So that's why Ig also can be taken as positive, but the I4 current is leaving from the junction B. So that's why I4 can be taken as negative and it is equal to 0. So what is the Kirchhoff's first law? The algebraic sum of the currents entering and leaving from a junction is equal to 0. So according to Kirchhoff's first law, the entering currents can be taken as positive and the leaving currents can be taken as negative. Is it clear? So that's why at junction B, I2 and Ig currents are galvanometer current, and current I2 is entered. So that's why both are taken as positive. But here I4 current is leaving. So that's why I4 can be taken as negative. This is at junction B. And at junction D, I1 is entered. This is, we can be considered as equation 1. So at junction B, at junction D, I1 is entered. That's why taken as positive. But Ig, I3 are leaving from the junction D. So that's why Ig and I3 can be taken as negative. Ig and I3 can be taken as negative. Is it clear? Is it clear? According to Kirchhoff's law, Kirchhoff's first law, junction rule, the entering currents to a junction can be taken as positive. The currents leaving from the junction can be taken as negative. So here at junction B, I2, Ig are entered currents. That's why can be taken as positive. I4 is leaving. That's why can be taken as negative. But similarly at junction D, I1 is entered. So that's why I1 can be taken as positive at junction D. But Ig and I3 are leaving. So that's why here Ig and I3 currents can be taken as negative. So here we got two equations from the application of the junction rule at the two junction point B and D. And in this Wheatstone bridge circuit, we have two loops also. So what are the loops? ABDA and BCDB. So here in Wheatstone bridge we have two loops, two junction points, and two loops are also there. So what are the loops? ABDA, it is one closed loop, and BCDB, whatever, or you can take CDBC, whatever it may be. So where you can start and then return back to that initial point, then you can complete one closed loop. Okay, so if you can start at C and you can finally you come to that point only. So if you can start at B, you finally come to at point B. So then also you can complete the total circuit. Okay, so here two closed loops are there. So one is the ABDA. So ABDA, so Kirchhoff's loop rule. Kirchhoff's loop means Kirchhoff's second law is applied. Kirchhoff's loop rule is can be applied for loops. First one is ABDA. Kirchhoff's loop rule is applicable for the two loops. We have two loops here, closed loops, ABDA and BCD or CDBC, whatever it may be, you can take. So what is the Kirchhoff's loop rule? So the algebraic sum of the change in potential around any closed loop is equal to 0. That is the Kirchhoff's loop rule. Already we discussed it in the previous classes. So here we can apply the in loop rule. You must in that class. So I told you you must and should remember two important sign convention conditions. What are those conditions? So if you goes through along the direction of the current, you can be taken as positive sign. If you go to the opposite direction of the current, you can take negative sign. You can take negative sign. If you can move from positive terminal to negative terminal for a battery, you can take negative sign. If you can move from negative terminal to positive terminal, you can take a positive sign. So those two important conditions are already we discussed. So here there is no cells are there, no cells are there, only resistors are there. So that's why if you can move along the direction of the current, you can take positive sign. If you anywhere, if you can goes opposite to the current, you can take negative sign. So here first of all the Kirchhoff's loop rule can be I can apply for loop ABDA. So I am starting from the point here. First of all I am starting from the point here. So here I2 R2, I2 R2. So I can move along the direction of the current. So that's why I can write I2 R2. So here I2 can be taken as positive. Why? Because I can move along the I2 direction itself. Okay. So that's why I can take I2 as positive. And here but I can move opposite to the IG, galvanometer current. So that's why I can take negative sign. I can take negative sign for galvanometer current. So first I2, I can move along the direction of the I2. That's why I2 can be taken as positive. So here I can write I2 R2. I2 R2 means IR means potential. What is the loop rule? The change in potential. So here potential means V. V means IR. So that's why I can write V equal to IR according to Ohm's law. That's why here I can write IR. So here I2 R2. I2 can be taken as positive, but we can move opposite to the IG. That's why I can take minus IG. Here capital G is the resistance of the galvanometer. Resistance of the galvanometer. And then so I can start from A, moves like this and moves like this and moves like this. So here also I can move opposite to the I1. Here also I can move opposite to the I1. So I can start from the point, I can start at point A and goes to point B, goes to point D, and again comes to the point A. Now I can complete one closed loop. So here I2 is the, I can move along the I2 only, but here IG and I1 I can move opposite to the IG and I1. So that's why I1 also can be taken as negative. So finally I2 R2 minus IG G minus I1 R1 equal to 0. So this is the first statement, first equation expression. So we get from the loop ABDA. So on the application of the Kirchhoff's loop rule. So now for the second loop for BCDA, so here I can start from the point B. I can move along the direction of I4 to the C. So here BCDA, BCDB. So here I can initially start at point B. So I goes to C and goes to D and goes to B and return back to B. So here I4 I can move here, I can move along the direction of I4. So that's why I4 can be taken as positive, and here I can move opposite to the I3. Here I can move opposite to the I3. So that's why I can take negative sign for I3, but here I can move, finally I can move along the direction of the IG. So that's why I can take minus IgG. This is the equation number 4. This is the equation number 4. So finally I can, so we have to apply the Kirchhoff's loop rule for 2 loops. Here we have 2 loops. One is the ABDA, another one is the BCDB. So for ABDA, if we can apply the loop rule, we get third equation. For BCDB loop, if we can apply the loop rule, finally we get the equation 4. So here we have to calculate the balancing condition. So whenever all the resistors are having same current. The same current is passing through the all the resistors. If the same current is passing through the all the resistors, then the galvanometer shows null deflection. That means the galvanometer current is 0. If all the resistors, the 4 resistors doesn't have the same current, then the remaining current, the excess amount of current will be passing through the galvanometer. Then the galvanometer shows deflection. So if the galvanometer shows deflection, that means all the resistors are not in balanced. Why? Because all the resistors does not have the same current. If the galvanometer shows deflection, if the galvanometer shows null deflection, that means galvanometer doesn't shows any reading, the galvanometer shows 0 reading, then we said that the galvanometer is the Wheatstone bridge is in balancing condition. Why? Because if Ig equal to 0, so the current passing through the all the resistors is same, so then only the galvanometer shows 0 deflection. So that's why, so here this is a balancing condition. So when the bridge is balanced, so if not we can write, so when Ig equal to 0, the galvanometer is current is 0, then the bridge is said to be balanced. The bridge is said to be balanced. So when the Ig, there is no current passing through the galvanometer, that means all the resistors has same current. The same current is passing through the all the resistors, then the galvanometer current is 0. Then we said that the bridge is balanced. So here, so when Ig equal to 0, that's why Ig can be taken as 0. So this Ig equal to 0 is substitute in all these 4 equations. So then what we get? So I2 equal to I4 and I1 equal to I2. So this is the 5th one, this is the 6th one. So from equations 1 and 2, from equations 1 and 2, so from equations 1 and 2, so we can substitute the value Ig equal to 0, then what we get? I2 equal to I4, I1 equal to I3. So here Ig equal to 0 means I2 minus I4 equal to 0, that's why I2 equal to I4. Here I1 minus I3 equal to 0, so that's why I1 equal to I3. From equations 3 and 4 what we get? So from equations 3 and 4, from equation 3 and 4 we get, so what we get if Ig equal to 0? So I2 R2 equal to I1 R1 and I4 R4 equal to I3 R3. So this is the equation number 7, equation number 8. So from equation 3 and 4, Ig equal to 0 means this total Igg is 0 and here also Igg is 0. So I2 R2 minus I1 R1, that's why I2 R2 is equal to I1 R1. Here also I4 R4 is equal to I3 R3. But why? Because Ig equal to 0. So from equations 3 and 4 we get I2 R2 equal to I1 R1, I4 R4 equal to I3 R3. So from this equation, so if I1 by I2, so from this one I1 by I2 equal to R2 by R1, right? So here I1 by I2, so I2 goes to right side, so and R1 goes to left side. Okay, so I1 by I2 is equal to R2 by R1, and from this what we can write? I3 by I4 equal to R4 by R3. So I3 by I4 here R4 by R3, R4 by R3. So from these two, but from equations 5 and 6, but from equations 5 and 6, I2 equal to I4, I1 equal to I3. So in any one of these equations we can substitute these values. In place of I2 we can substitute I4, in place of I1 we can substitute I3. So then what happened? LHS are equal. So from equations 5 and 6, so this equation can be I3 by I4 is equal to R2 by R1. So this is the equation number 9 and this is the equation number 10. This is the equation number 9. So here from equation 5 and 6 what we get? I2 equal to I4, I1 equal to I3. So here in place of I2 and I1 we can substitute I4 and I3 here. So then this equation can be turned as I3 by I4 equal to R2 by R1. So but here equation 9 and equation 10 LHS are same, therefore RHS are equal. So therefore from equations 9 and 10 LHS are equal, therefore RHS equal. So therefore finally what we write? R4 by R3 equal to R2 by R1. R4 by R3 equal to R2 by R1. So this is the final expression for the Wheatstone bridge balancing condition. So R4 by R3 equal to R2 by R1 is the balancing condition for Wheatstone bridge. So finally what we get? R4 by R3 equal to R2 by R1. So here you must and should remember, here R4 is the unknown resistance. So the unknown resistance wire is connected to at R4. Then using this condition R4 equal to R2 by R1 into R3. Using this condition R4 equal to R2 by, from this is R4 equal to R2 by R1 into R3. We can calculate the unknown resistance of the wire, given wire. So if you anybody given to some wire and calculate the identify the resistance of that wire, then that wire you can be connected at this place R4. Then so R4 is that's why we call it R4 is unknown resistance. But here R3 is the known resistance. Why? Because here in place of R3 we can connect the resistance box. So in place of R3 we can connect the resistance box. So why? Because resistance box, in that resistance box, so we keeps on changing the resistance of the resistance box. So then at some resistance of the R3 known resistance, the bridge is balanced. Then we get the condition from the condition R4 by R3 equal to R2 by R1. So we calculate the unknown resistance of the given wire. So here R4 is the unknown resistance. R4 is the unknown resistance. So the unknown resistance wire is connected at place of R4 and the known resistance means resistance box is connected at R3. So then using this balancing condition, so we can calculate the unknown resistance of the given wire, that is R4. So this is the use of Wheatstone bridge to to calculate the unknown resistance. So we can use this Wheatstone bridge balancing condition. So here so I can miss a small point, that is galvanometer. So what is the galvanometer? So galvanometer is a very sensitive device. It is a very sensitive device. Galvanometer is a very sensitive device. So why we need to connect the galvanometer here? Galvanometer is a very sensitive device. It measures the very small currents also. As well as very small potential also. Galvanometer is a sensitive device. It measures It measures voltage, that means potential difference, and also the current. It measures voltage, and also it is used as a voltmeter, and it is used as a ammeter. What is that? Galvanometer. But it is a very sensitive. So for, if you can use ammeter or voltmeter, so that is ammeter and voltmeter are not, or a ammeter and voltmeter not a sensitive device. Why? Because, so if you can use ammeter or voltmeter, you can calculate the reading minimum above the 1 ampere or 1 volt. So less than the 1 ampere or less than the 1 volt, you can't measure. The readings by using the ammeter and voltmeter. But very small currents or very small voltage are also can be measured by the sensitive device galvanometer. So that's why here we connect the galvanometer to the two junction points B and D. So that is the use of galvanometer. So very small current or very small voltage, if 0.1 ampere current or 0.1 voltage are also can be measured by the galvanometer. So that's why we connected here galvanometer. That is the use of galvanometer. So this is about Wheatstone bridge. Very important question for 8 marks, and it is also very important for MSET, JEE, NEET also. So is it clear? So we Kirchhoff laws, and the application of Kirchhoff laws is Wheatstone bridge, and finally we got the balancing condition for the Wheatstone bridge. So what is the balancing condition? R4 by R3 equal to R2 by R1, or R3 by R4 equal to R1 by R2, whatever it may be. So finally here R4 is the unknown resistance, R3 is the known resistance. Using this known resistance, we can calculate the unknown resistance value using this Wheatstone bridge. So this is about Wheatstone bridge. Very important question. Is it clear? So I think all of you is very clear. Thank you. This is Kranthi signing off.